Hello everyone, welcome back to my channel Deep Understanding of Research Papers. Today in this tutorial I will explain a new paper which was released yesterday by Apple. It's called Bandwidth Embeddings for Mixed Bandwidth Speech Recognition, and the authors are here. These guys are working in Apple, and Apple recently started publishing their papers into the community. Like now we can read their papers, and the tutorial will cover the overview of the paper. Then we will see what are these bandwidth embeddings for acoustic modeling training. Then we will see something called parallel convolutions, which are used in this paper to get some improvements in accuracy. Then we will see some experiments and data sets, and finally we will see some results. So what is the aim of this paper? So basically the aim is to extract something called bandwidth embeddings. So first of all, what is bandwidth? What are these? What is the idea of this paper? So basically, when you have any speech problem, for example, let's say speech recognition, language ID, or accent recognition, whatever. So you will have particular data set which is recorded in some frequency, some sampling frequency. So assume you have, let's say, narrow band, wide band signal. So wide band is basically assume is a 16 kilohertz, narrow band, let's say 8 kilohertz audio. So basically these audio files are recorded at different sampling frequency, and if you train your model using, let's say, wideband audio data and test it with narrowband data, you will get very poor performance. Basically your model will give some junk output, so which is not a good thing. In the same way, if you train your model using narrowband data and directly feed 16 kilohertz audio files during testing, you will get very bad outputs. So what are these problems? Because why this happens is because the frequency content changes completely. Whatever frequency content the model sees during training, it will not be able to generalize it to the test data which is of different band. For example, let's say wide band if you train your model with narrow band. So these are the problems people face. Even I have faced it many times. If you train your speech recognition model and if you want it to generalize to all bands, basically all kinds of audio data, let's say telephone, news recordings or studio recorded audio, those kind of things, then you will have to train you have to be very careful about how you train your model. So basically you could simply mix all the data and train a model, but it might not be as good as like for example this paper. So you have to introduce new tricks so that the model will be able to take care of these domain mismatch. So domain in the sense different bandwidth audio signals. So these guys are going to train something called mixed bandwidth audio acoustic model, which is basically robust for any other bandwidths, and we will see how they have done that. So basically they use something called bandwidth embeddings to take care of these bands. I mean audio data from different frequency range or sample frequency. And also these guys have introduced something called parallel convolution layers to take to process both narrowband and wideband signals at the same time and generate some representation which is shared between those two bands. We'll see how those things works in the coming slides. And this case gets 13% relative improvements over narrowband speech signal while not degrading about wideband. So usually if you train a narrowband model and test it with a wideband model, you will get very bad output. I'll be very happy if I train a model which gives me 90% accuracy on the same domain data, but same 90% accuracy on the other domain data also. So it's okay to get the same accuracy for both of them, but it should not worsen the performance. So we will see how the bandwidth embeddings are used for acoustic model training. Assume this is some sort of look at this as some sort of acoustic model which does not use the bandwidth embeddings. And basically this model, if you look at it, it has some convolution layer, some max pooling and convolution, and it has some dense layers, and it has some bottleneck and then output. Assume they are not completely explained how these outputs are calculated and how they propagate the loss and all. This basically might have some CTC head or something. So CTC loss, with CTC loss they might be able to train this model, but the details are not given in the paper. Assume some sort of prediction of the labels or characters or phonemes, and given that this is the model CNN plus DNN model, Now, how do we incorporate the bandwidth embeddings is like this. Assume we take some dense layer vectors here, and this to this dense vector we are going to append some other vectors, some other sequence, some other let's say a feature vector which is basically called bandwidth embeddings. So, what are these bandwidth embeddings? So, basically when we feed when we feed the input, we will know whether it's wideband or narrowband. For wideband, we send c equal to 0, and correspondingly we'll have some vector here. This vector is trainable vector, so just like the trainable embedding layer we have in for example we use in NLP or something. So the same thing, we have trainable bandwidth embedding layer, which basically takes 0 or 1, which says basically 0 narrowband and 1 wideband, and it gives concatenates those vectors into these dense layers, and remaining things are similar. So before you had this equation where, for example, assume this is the layer L, and we take output from layer L minus 1, multiply it by some matrix W, which is the weight matrix here, and add it with some bias term, and feed it through some activation function something, and this output OL does not have any bandwidth embeddings here. But now what we do is we take the embedding E, which is basically initially random, but later it is learned, and this vector goes through some transformation, and that vector, this becomes a vector, and that gets added to the bias vector. So basically the new bias is basically B cap. So this is how you add the bandwidth embeddings to the model. Very simple idea, right? So these embeddings are trainable. Now, given that we will get some good accuracy using that model, like trainable embedding model, but these guys have introduced something new, which is basically wideband signal will be of 16 kilohertz, and their frequency range will be 0 to 8 kilohertz. And you will get, if you for example compute let's say filter bank energies, you might get around 27 filter bank energies. And if you use narrowband signal, you might get around 22 filter bank energies. That's what they have said in the paper. Now there are some few filter banks missing. So instead of feeding both these signals into the one single convolution, why can't we just process the wideband speech in one stream and a narrowband speech in another stream? Basically, this is another convolutional neural network, and this is a separate convolutional neural network. Both of them will have different filter sizes. These two are not shared. Right? These two are not shared at all. This is a separate network. This is a separate network with separate its own filters and basically its own convolution filters and max pooling layers. And finally, after the convolution, we'll mix the outputs from both of these two in a single dense layer. Then whatever bandwidth embeddings we have will go into the dense layer. So basically, it's not completely shared architecture, or not exactly a different separate stream architecture. It's basically sort of a two-stream model. At the end we fuse, or at the end we combine both of these representations, something like that, right? So this is how the parallel convolution model works. And coming to the data set, this is Apple's paper. So they will have their own data set. They have wideband data. They have around 2023,000 hours of sentences with hours of data, 3,400 hours of data. These are number of utterances. And for narrowband, they have very less amount of data. Basically, the wideband is very big compared to narrowband. And evaluation, for the evaluation, they have 50,000 hours of data for evaluation. Not 50,000 hours, 54 hours of data, 4 hours of testing data, and these are the utterances. And coming to the architecture side, they have 7-layer neural network. Basically, first 2 layers are just CNNs and convolution layer, and second layers are the next 4 layers are dense layer with one output layer, and every layer will have activation function as CELU. So the CELU is basically self-exponential linear unit, something basically invented back in 2017, if I am not wrong. So this CELU is basically invented by Sepach writer. That paper is a well-known paper, and people are using this CELU just like ReLU. So it adds its own properties. It's good. People can use it. And coming to the convolution side, those are the just number of filters and so on. And if you see, the dense layer has 1024, bottleneck layer has 512, and output layer has around 8,000 units. So basically, these output units may be just the subwords, basically, right? And coming to the input side, they have 40-dimensional log filter bank energies. with left and right context of 10. Basically, they stack all of these left 10 and right 10 the left 10 and right 10 vectors, and they feed it to the model. And model is trained using cross entropy loss function, obviously, right? So coming to the results, so let's just get the model names properly. So AM1 basically stands for model trained with wideband data, which is that the 3600 hours of data. And AM2 basically is a narrowband model, basically trained only with narrowband data, right? And if you see the word error rates for only wideband data for AM1, you get 13%, which is decent. But if you test that model with the narrowband data, you can't directly test this. You have to do upsampling because it's 8 kilohertz. Subsample it, and you get this much, right? And if you train narrowband data and if you use wideband signal, if you will get 22%, which is bad. And testing with narrowband itself is 22% because the amount of data itself is low, right? Maybe because of that reason. Coming to EM3 is basically combining WB1, wideband and narrowband, simply mixing them together and just testing with these two. I mean, we get still it's bad. And EM4 is basically downsampling or upsampling NB1 to 16 kilohertz and combining with the wideband, and still it doesn't give you that much improvement, right? So this is how the systems are, and this is how the accuracy are. Coming to these guys experiment where they just combine the bandwidth embeddings with the acoustic model, basically the dense layer. If they just add it, they get a little bit improvement over both, and even AM4 you get a little bit improvement, right? Not that great, 2% for example, right? And if you add convolution, parallel convolutions to these AM3 and AM4, you get the state of the art. So for example, here you get the best model. Sometimes in AM4 you get only embedding only based one is little better than the parallel convolution based one. And also they have also measured some accuracies with increasing the dimensions of the bandwidth embeddings, and for 128 bandwidth embedding size of 128, they get the best accuracy for both wideband and narrowband. And that's all for this tutorial. Thank you so much for watching this tutorial. If you are not subscribed to my channel, please subscribe for more video content. Thank you.